Good afternoon, everyone. I'm Tomohiko Hojo from Tohoku University. Today, I would like to talk about hydrogen embrittlement properties of microalloyed trip-aided martensite Bainitic ferrite steels. First, I'm going to explain the background. In ultra-high strength low-alloy trip-aided steels with Bainitic ferrite matrix, TBF steels, it has been reported that TBF steel possesses high strength and excellent ductility and press formability owing to the transformation in this plasticity of retained austenite. And TBF steel enhances the hydrogen embrittlement resistance because of the high hydrogen absorption capacity of retained austenite. To further improve the hydrogen embrittlement resistance of ultra-high strength low-alloy trip-aided steels, it is expected to add the alloying element to the trip-aided steel to refine the microstructure, to enhance the hardenability, and to precipitate the carbide acting as hydrogen trapping site. Also, addition of alloying element expected to improve the retained austenite characteristics of the trip-aided steels owing to the transformation in this plasticity effect and absorption of hydrogen. About the previous report, in the trip-aided martensitic steels, TM steels, microalloy TM steels decrease the hydrogen embrittlement susceptibility. So it is expected that the hydrogen embrittlement resistance may be enhanced by the partial replacement of the martensite to Bainitic ferrite, because bainite or Bainitic ferrite possesses excellent resistance to hydrogen embrittlement. So in this study, to develop the ultra-high strength automotive frame parts with tensile strength of more than 1180 megapascal, effect of alloying elements on hydrogen embrittlement properties of ultra-high strength trip-aided Bainitic ferrite martensite TBM steel are investigated. Next, I'm going to describe the experimental procedure. In this study, 6 kinds of steels with chemical compositions as shown in this table are used. Steel A was base steel, and titanium, boron, chromium, chromium molybdenum, and nickel, chromium molybdenum were added to the steel B to F. Heat treatment was conducted by the annealing at 920 degrees Celsius for 1200 seconds, followed by the isothermal transformation treatment at 350 degrees Celsius for 1000 seconds to produce a TBM steel. Tensile tests are conducted using a tensile specimen with dimensions of 15 millimeter in gauge length, 6 millimeter in width, and 1.2 millimeter in thickness at a strain rate of 8.33 by 10 to the minus 4th power per second. hydrogen embrittlement properties are evaluated by the hydrogen embrittlement susceptibility, HES, using this equation, in which epsilon 0 and epsilon 1 denote total elongation without and with hydrogen. The hydrogen charging was conducted by the means of cathode charging using a solution containing 3% sodium chloride and 3 gram per liter ammonium thiocyanate at a current density of 10 ampere per square meter at 25 degrees Celsius for 48 hours before tensile test. Next, I'm going to show you results. This figure shows the microstructure of TBM steels. In the steel A, the microstructure of steel A consisted of a Bainitic ferrite and Martensite matrix with a grain diameter of approximately 20 micrometer and retained austenite. On the other hand, in the microalloyed TBM steels, the fine Bainitic ferrite and Martensite matrix were observed. Although we could not distinguish the Bainitic ferrite and Martensite, the amount of Martensite increased by the addition of alloying element. This figure shows the tensile properties and retained austenite characteristics of the TBM steels. The tensile strength increased, and whereas total elongation slightly decreased by the addition of alloying element. Volume fraction of retained austenite increased, and its carbon concentration decreased in the steels D, E, and F. This figure shows the nominal stress strain curves of steels A, C, E, and F. You can see that the stress strain response, such as yield strength, the maximum strength, and work hardening behavior, was hardly changed by the hydrogen absorption. In steels C and E, the fracture strain decreased significantly by the hydrogen charging. On the other hand, the fracture strain of steels A and F hardly changed by the hydrogen charging. This figure shows the relationship between hydrogen embrittlement susceptibility, HES, and tensile strength, yield strength, and elastic limit. The hydrogen embrittlement susceptibility increased by the addition of alloying element, and HES increase with increasing tensile strength and elastic limit. In addition, HES significantly increased when yield strength exceeded 1100 megapascal. These figures show the hydrogen desorption curves and relationship between hydrogen concentration and volume fraction of retained austenite in the TBM steels. The hydrogen concentration calculated from the hydrogen desorption curve are also shown in the table. The hydrogen was dissolved at the temperature between room temperature to around 150 degrees Celsius. And peak temperature was approximately 50 degrees Celsius. And alloying element addition increase the peak temperature to peak temperature. And high amount of dissolved hydrogen were observed in the TBM steels with alloying element. From the right-hand side graphs, we can see that hydrogen concentration increased with increasing volume fraction of retained austenite. This result suggests that a large amount of hydrogen trapped in or around retained austenite. Next, these figures show the relationship between hydrogen embrittlement susceptibility and retained austenite characteristics, such as volume fraction of retained austenite, carbon concentration in retained austenite, and total carbon content in retained austenite. You can see that HES decreased with increasing carbon concentration in retained austenite. However, the significant tendencies are not observed in the volume fraction of retained austenite and the total carbon content in retained austenite. Carbon concentration corresponds to the stability of retained austenite. Therefore, high carbon concentration possesses high stability of retained austenite, and retained austenite transformed to martensite in the later stage of tensile test. In our previous report, when tensile test was conducted with hydrogen, the retained austenite transformed to martensite. The crack initiated at the transformed martensite. Therefore, the crack initiation and propagation was accelerated in the trip-aided steels. If crack transformation of retained austenite occurred. Therefore, hydrogen embrittlement resistance of trip-aided steel decreased. The factor affecting hydrogen embrittlement resistance in trip-aided steels were strength, microstructure, hydrogen concentration, stability of retained austenite. In the microalloyed TBM steels, microstructure was refined and volume fraction of retained austenite increased. These factors decrease hydrogen embrittlement susceptibility. However, the strength increased and carbon concentration decreased and hydrogen concentration increased in the microalloyed TBM steels. These factors increase hydrogen embrittlement susceptibility of the TBM steels. Therefore, these factors simultaneously affect the hydrogen embrittlement susceptibility and hydrogen embrittlement susceptibility of the microalloyed TBM steels significantly increased. The conclusions of this presentation is as follows. Thank you very much for your attention.